Hello, this is Concrete Path. Today, your lecture would be dedicated to moment area method. Before that, we have one problem left from Castigliano's theorem. So let's go and solve that problem on Castigliano's theorem. Say this is a frame structure is there, and a UDL of 4 kilonewton meter, 4 kilonewton per meter is acting for a length of 10 meter. For a length of 10 meter, UDL is acting. So this is A, this is B, and this is your support C. And here it is a roller. Similarly, it's your 2I. This is your I. And you need to get the horizontal displacement at point C. For the Castigliano's theorem, we say there should be some load acting at the point where you want to find the deflection. Let's say you have to get the deflection in horizontal direction at C, so you need to apply a pseudo load of H. So you need to apply a pseudo load of horizontal H in the direction of horizontal displacement at C. So let's calculate the reactions. Then after that we will take section X, then we calculate moment at any X. After that we have the delta equation. So we can say summation of forces in horizontal equals to 0. So your reaction at A would be equals to 44 into 10 plus H equals to HA, 40 plus H. So your horizontal becomes 40 plus H. So if you take summation of moments at A goes to 0, you can take reaction here C, at reaction here A. You can take summation of moments at A equals to 0. Then you can say your C into your length was 8 meter, C into 8 anti-clockwise plus UDL of 4 into 10, 10 square by 2 equals to 0. Yeah, then there is also a horizontal that force. So horizontal reaction H into 10 moment, H into 10 plus H into 10 equals to 0. So reaction C becomes equals to 25 plus 10 by 8 of H. So you got a reaction of 25 plus 10 by 8 of H. So you got the reaction. Then next step is to get the moment at any X in the segments. So let's take that. Let's take from this support C, we go at any X. There is some moment X, mx. So this is your X. And similarly in the span AB, we go from support A to any point X. There we calculate moments at that point X. Can we write the equation? Let's take for the segment. Let's take for the segment CB. The range for the value of X is from 0 to 8 meter, and we can write moment at any X. Moment at any X, this one. By the summation of moments at X equals to 0, we can write mx is clockwise positive. Then we have effect of this one, that's anti-clockwise. That's anti-clockwise reaction 25 plus 10 by 8 of H and into X equals to 0. So we get the moment at any X equals to 25 plus 10 by 8 of H into X. Let's say you want to get the small m. The small m we write as dou mx by dou H, because your H is that pseudo where you want to find the delta. So it becomes equals to this one is 0, so it becomes 10 by 8 of X. 10 by 8 of X. Finally you got the moment mx and small m in the segment CB. Similarly, we can get in the segment BC, segment AB. Range of the X is from 0 to 10 meter. So we can write moment at summation of moments at any X equals to 0. So we can write moment mx is anti-clockwise. Here the moment mx is anti-clockwise, and you have, since the horizontal reaction it has an effect on the moment mx. We can write 40 plus h into x, and you have a UDL of that 4x square by 2, but it is anti-clockwise about the x, 4x square by 2, and effect of this reaction A, it is along the axis, so its effect is not there, so we can write equals to 0. Then your moment mx becomes equals to 40 plus h into x minus 2x square. Let's say you want to get the small m. Your small m equals to dou mx by dou h. That becomes equals to x. So finally, if you want to find the delta horizontal at c, you can write delta horizontal at c, that equals to 0 to, let's take the effect of this one also first. The range is from 0 to 8 meter. We can write 0 to 8 meter. The value of moment, and say here is a variable, here the variable is h, but we don't know the value of h. We say set the value of h equals to 0, because we have applied h equals to 0. So we say set h equals to 0 directly to avoid the calculations. We can get the equation then 25 into x into small m is your 10 by 8 of x, and dx by ei. Similarly, for the next case, for the segment AB, we go from 0 to 10 meter, and so, here we also set h equals to 0. Let's say this part goes to 0, so we are left with 40x minus 2x square into small m, that's your x, and dx by ei. And we can calculate this integration part, so we can get the values, and you can say that 25x square. Yeah, you can calculate it directly. You can get the delta sc. You have also given that e and I, values of e and I. Let's say you got the value as positive 11000 by ei. A positive value here means that the direction you assumed that horizontal, you applied a pseudo load of horizontal h in the direction of positive x-axis. So that means your positive value means the deflection at c in the horizontal is also in that same direction, in the direction that you applied the load h. The final diagram would be somewhat, say this one is going this far, this point, then this would deflect somewhere here. This was the end of our Castigliano's theorem. It's having a more scope. Castigliano's theorem is having more number of problems, but we are following that. Let's keep that part in the structural analysis. There we say we solve that indeterminate structures using Castigliano's theorem. Our focus here is to majority of the time we'll be focusing in determinate structures in the strength of material. So this was the end of the Castigliano's theorem. Now we are left with moment area method. Let's go for the moment area method. Let's write moment area method. So you have a beam, say general beam of, let's say this is your general beam, and you have general loading of, say this is your general loading, this is loading, and you say we have two reference points, say point 1 and point B, point A and point B. Then you do one thing, you have that you got BMD, you can get the BMD from the loading. Once you got the BMD, then you say the BMD divided by EI, that's M by EI diagram, along the length of the member. You plot the variation, say this is your BMD diagram, and you say, let's say I want to get the theta difference between the two, slope difference between the two. How can I get it? And let's say I want to get the difference between the two in the deflection profile also. I want to say what is the difference between the deflections of the 2 points and slope difference between the 2 points. It says that the moment area method, it has two theorem. Your theorem number one says that let's say you go to a point dx. Let's say you go to a point x, you take a strip dx, you have that d theta by dx equals to m by ei. Let's say you have that d theta equals to m by ei into dx. Let's say you integrate it from point A to point B, and this one also from point A to point B. So you get that point A and point B. There is some theta and delta, so we can write theta B minus theta A equals to m by ei diagram area. So we can write m by ei diagram area between A and B. So this is the theorem one that says that slope difference between the 2 points, that equals to the moment m by ei diagram between the 2 points A and B. Slope difference between 2 points equals to m by ei diagram area between the 2 points A and B. So it says that once you got the point A and point B, if you want to say what is the theta difference between the two, get the area between the 2 points in the m by ei diagram. That the area we got in the m by ei diagram between the 2 points A and B is your theta B minus theta A. So we write it as theta forward minus theta backward, theta forward minus theta backward. So we are going from this one to this one, 0 to x in the positive x-axis. So we write this was your forward, this one is your backward. So write theta forward minus theta backward. That is equals to area between points B and A and B. Okay, this is your theorem number one. Let's have the theorem number two that says once you got that theta between the 2 points, that's area. Then we say that the difference between, we write it as that we write deflection at B. We write deflection at B with respect to the tangent at A. That equals to centroid or moment of area about point B. Moment of area about that point B. So moment means the centroid of that area about the point B. That's centroidal distance of that area. Centroidal distance of that area between A and B, but that should be about point B. And this statement means deflection at B with respect to tangent at A. If you draw tangent from A, then you say that with respect to that tangent at A, what's the deflection at B? So that equals to the centroidal distance between centroidal distance of that area between the points A and B, but that centroidal distance should be about that point B, about which you have to calculate that deflection. Delta B, here it should be centroidal distance about point B. So this is your theorem number two. So let's say if I write delta AB, let's say I write delta AB, that means deflection at A with respect to tangent drawn from B. Generally, if we say generally delta A with respect to B is not equals to delta B with respect to A. It is general case. It can be equals if the loading is symmetric or the supports are same and loading is symmetric, we can say then at that time they can be same. Let's say this was your general deflection profile. You want to say this is your point. Let's say this is your point B, this is your point, this is your point. Let's say this is your point A. This you got as deflection at A. This you got as deflection at B. Let's say you are drawing a tangent from, let's say you draw a tangent from A. We can write it as tangent from A. So now this line, this delta, we can write it as this is the deflection at B, but it is with respect to the tangent you draw from A. Similarly, if you want to draw a tangent from B, let's say you draw a tangent from B. Let's say this is your tangent from B. We can write it as this one is a tangent This is tangent from B. So we would say, what is this value? What is this value? We can write it as this is the deflection at A, but it is with respect to the tangent you draw from B. So we can see that your delta A with respect to B is not equals to delta B with respect to A. Generally, we can write generally. It can be same also. So let's have the problem. Say we can take the problem number 1 on this method, and you have to remember that the two statements that this moment area method is valid, is best suited, it can be used if EI changes. That means if the member is non-prismatic member, that means E and I changes. If your E and I changes along the length, then you can use this method also, because it accounts that M by EI. So your diagram includes E and I, so your effect of E and I is also contributed there. Then if you have Macaulay's method there, the EI d2y by dx2 we had equals to some moment mx. There we said that EI should be constant. It was only applied to prismatic beams, where the EI was constant. So moment area method is an advantageous. It is an advantage over that Macaulay, we can say. And next point about the moment area method is that it has some limitation also, that when we write delta B with respect to A, that means if you had deflection with respect, if you want to find deflection with respect to deflection at B with respect to point A, the point A should be, we call it as a reference point. When we say with respect to B, with respect to A, that means this point A is a reference point. Its delta should be known. We should know the delta at A. Then and only we can easily calculate moment area method using moment area method, that deflection at B. So similarly, if you have delta A with respect to B, that B is your reference point. It is deflection. We should know that deflection value. Let's say the method moment area method is helpful if the beam is, say, cantilever beam, or at a fixed beam, where we know that if we take say A point as reference, we know that if we draw a tangent from A, here the delta is 0 and theta is also 0. So moment area method is helpful if the reference point, we write, if the reference point is say a fixed support, and a reference point should be also that we can take that, say you had UDL, deflection profile is somewhat this way. We know that at the point where the delta is maximum, at the point where delta is maximum, theta is 0 there. So we can say we can draw a tangent also here. So we can say this point also, that point, that midpoint, we can write midpoint of symmetric beam, because there the delta is saying that the theta is 0, midpoint of symmetric loading beam. So reference point should be, so the conclusion is reference point should be that point where the theta or delta is known to us. Then accordingly we can get the value of theta B and that theta and that delta. Okay, let's have first problem. Let's have problem number 1. Say you have a non-prismatic beam for length 3 meter. You have area moment of inertia that I equals to I, then you have here 2I. Then what you do, you apply anti-clockwise moment of 500 Newton meter. Then you say that get the value of deflection at B and deflection at C, where your point B is here and point C is here, and this is your point A. So your moment area method says that you need M by EI diagram, that means BMD by EI, and you need centroids, and you need that you need reference point. So let's go. Let's say let's follow step by step. Say we can get BMD for this beam. So we can directly say BMD should be a constant value of positive. Say here the moment developed would be clockwise moment 500, and it would remain constant because no shear force is acting anywhere. So we can write 500. This is your positive 500 BMD. But we don't need BMD. We need M by EI. We need M by EI. So let's take in terms of M by EI. Say this was your 500. When you 500, we can write here 500 by E, 500 by E into I. Your I value here is 2I. So it becomes 250 by EI. So we can write this is your 250 by EI up to this point. 250 by EI. Then after that, your I changes from 2I to I. So we can write 500 by E into I. So your value becomes 500 EI. So your value rises by 500, 250 also more. So finally your value becomes here 500 by EI. So this is your, we can write here, this is M by EI diagram. So once we got this one, we can get the centroids also. We know that centroid here, and this one is centroid here. But what should be the reference point? Which one should we take the reference point? Let's say let's convert it in terms of a line member. Let's say this is a line member. You are applying a moment of M. Where the beam should deflect because of that anti-clockwise moment. Let's say this is our fixed support. You are applying an anti-clockwise moment. That's beam trying to deflect upwards. So beam tries to deflect upwards. Let's say beam tries to deflect upwards. So here we know that at point A, theta is 0 and delta is 0. So can we take it as a reference point? Yeah, if we can take it as a reference point. Let's say if we draw a tangent from A, then we say that this is point B. Here the delta, it should be delta B, and here the point C, it should be delta C. But the one more thing is that once you draw tangent at A, tangent from A, then we can use moment area method. It says that what should be this value? If you draw tangent at A, what should be this value called as? We can call it as delta deflection at B with respect to the tangent you draw from A. Similarly, we can call it also as deflection at C with respect to the tangent at A. Can we say that? Yeah, we can say that. So if you want to say what is the value of deflection at B, we can write that's also called as deflection at B with respect to the tangent at A, that equals to, from the theorem 2, that is from the moment area method theorem 2, it says that equals to centroid of the area between A and B about the point B. Why do you want to find the deflection into area between A and B? So we need to get the centroid of the area between A and B. We have the area between A and B, that is equals to this one. So this is your point B, this is point A. The area between the 2 points is this one, 250 into 4 meter, 250 into 4 meter. We can write your area of 250 by EI into 4 meter, and this is your kilonewton meter or Newton meter, whatever. You can check the units later. So we got this value. What should be the centroidal value? That xb. That means the centroidal distance up to centroidal distance of the area about the point B. That's equals to 4 by 2. That's 2 meter. So we can write 2 meter. Can write 2. So finally you can calculate that. So if you want to substitute the value of E and I, then accordingly you can get the value of E and I, that deflection at C. That here we can say it is 250 into 8, that's 2000 by EI. Then accordingly the units of E and I would be somewhere, some values, and let's say this was your kilonewton, let's say this was your newton meter, and length was also meter, and this was also meter, so we can write meter square also. So it depends on the units, then you can calculate after that. Once you got the delta B, now you want to find the delta C. So similarly, we can apply a moment area method between the 2 points A and C. So we can write delta C equals to delta at C with respect to the tangent at A. This value, we know this is equals to centroidal distance of the area between A and C, and about that point C into area between A and C. Area between A and C. What is the area between A and C? Since see here the area, we have two area. One is your smaller area, next one is your bigger area. So we need to get the centroid, separate centroids, and then we do summation of those moment into area. So we're at 250 into, so now we need to get the centroid about the point C, because we are finding the deflection about point C. So we need to get the centroidal distance about point C. So we can say this is your 3 meter plus 2 meter, that's 5 meter, and this one, this is your 1.5 meter. So we can write 250 by EI into 4. So we can write 250 by EI into 4 meter into 4, acting at, why it is acting? It was acting at, I think, 3 plus 4 by 2. That's 5. 3 plus 4 by 2, that's 5. And similarly, we have this 500 into length of 3 meter, 500 into 3, and it acts at 3 by 2. So we can write plus 500 by EI into length of 3, acting at 3 by 2. So we can get the value of deflection at C. Here we would be getting deflection at C positive and deflection at C also positive. That means the direction with respect to the positive value here means positive value means that the point C has shifted. That means point C and point B are above point A, are above reference point A. Because your tangent, you draw the tangent from A. So your point A has reached here and point C has reached here. So we can say point A is above your reference and point C is above your reference. So we write it as positive. Similarly, we can take now next problem, that's a simply support beam. We have a simply support beam and a load is acting at the midspan. This is your L by 2 EI, it remains constant. So we can get the delta maximum and theta maximum. Say if you draw the deflection profile, we can say loading is symmetric. If the loading is symmetric, we can say delta is maximum at mid and theta would be at ends. We can see that from the deflection profile. Say here we can say delta is maximum. We can name it as ABC. We can say delta, this is your delta maximum, and at that point there is a theta that is 0. And here we can write theta is 0 at mid. For if the loading is symmetric. This is only valid if the loading is symmetric. Delta at mid can be 0. Once the delta at mid is 0, we can take that point as a reference point. Let's take that as a reference point and draw a tangent drawn from point C. This is your tangent drawn from point C. Then if you want to say what is the delta max, we know that delta max is here, but if we take itself as a reference point and we do some tricks, we can say, if you want to say what's this value, we can write it is the deflection at A, but it is with respect to the tangent drawn at C. It is also equals to the deflection at B, but with respect to the tangent you draw from C. But that is also, if we analyze that, this value, this is also equals to this value. So we can say, if you want to say delta C, we know that delta C is delta max, but see the direction, delta C is downwards. So we can write magnitude of delta C is also delta max, but it's downwards, and it's also equals to delta at A with respect to tangent at C. If you want to find delta at C equals to what, we can say get the M by EI diagram and check the centroid. So we can say we can make the BMD now. Let's say the BMD would look like at the midspan, a point load, we can have that BMD equals to PL by 4 and you divide by EI, so your M by EI diagram. This is length L by 2, this is L by 2, and we need to get, we write that delta at A with respect to tangent at C. So this is point A, this is point C. So we only need to get the area between the 2 points A and C. So this is our area. And the centroid, for the centroid we need it from point A because we are finding deflection at A. So from the point A, this is our centroid. So this is our X, okay, right, XA, centroidal distance about A between the 2 points A and C. What's the area between the 2 points? We can write that equals to area between the 2 points. We can write that 1 by 2 PL by 4 EI and length of L by 2, and this acts at your XA bar, that equals to 2 by 3rd of length L by 2, 2 by 3rd of L by 2. So you can get the value. So we can get the value as that positive PL square by PL cube by 48 EI. So this is our delta A, but if we say that what's the value of delta A in the actual scenario, we say delta A is 0 because it is supported here, it can't go anywhere. But the thing is, we got delta A with respect to tangent at C. So we can show the sign that delta A is upwards with respect to the point C. If you got positive, that means point A is upwards, point A is above your reference point C, above point C, reference point C. If your point A is reference, if your point A is above reference point C, that means your delta C is negative PL cube by 48 EI. That means point C is downwards with respect to A. That means it should be negative value of PL cube by 48 EI. That means a deflection at mid should be downwards PL cube by 48 EI. Similarly, now you want to get the theta max. So we can erase this part now. We want to get the theta max. We want to get the theta max. We want to get the theta max. We want to get the theta maximum. Let's say you want to get the theta max. We can say for the when there is a simply support beam subjected to a load that is symmetric, we know that deflection at mid equals to 0. And if we say what's the deflection at any point from x dash from point B, we say that at that point there is some theta 1, that's summation of small d theta contributed by small those strips of dx, these strips up to that point x dash. So summation of all those strips. So what we say that what should be the value of theta at the ends? We write summation of all those theta contributed by those small dx strips, and you sum them from the midspan up to that point, you can get the total deflection. So we can write theta is maximum at the ends. Your theta is maximum at the ends. That's also theta at A. So we know that theta at mid is equals to 0. So if we draw, let's say you want to find that, we know that the representation of theorem 1 is like this, that theorem 1 says that theta forward minus theta backward equals to area between the 2 points, But your theta forward minus theta backward is like you have point C, it is your forward point, so we can write theta C minus theta A. We also write it as this way. This is our theorem, that theta CA, this is theta C minus theta A, that is area between the 2 points, CA. The notation of this one, the meaning of this one is that means that means slope at C with respect to the tangent drawn from A, tangent at A, tangent drawn from A. So he says you draw the tangent from A, you see what's the slope with respect to that tangent at C, then that would be calculated as the area between the 2 points. So we need to get the theta CA, but the tangent should be from point A. So if you draw a tangent from point A, let's say it's our point. Let's say it's our tangent from point A. We know that here the theta is theta at A, but here the theta is 0. So if we say this is our that line, that theta is 0 at C. If you want to connect to the 2 points, but you have to connect it with respect to the tangent you draw. You are drawing tangent from A, so you have to connect it from tangent at A. So this is our tangent at A. You have to connect it from the tangent at A. It is anti-clockwise. So we can write this value is equals to theta at C with respect to tangent drawn from A. This is equals to theta C minus theta A, and that equals to, from the third one, that equals to area between the 2 points. That is equals to area between the 2 points. What's the area between the 2 points? That triangle between the 2 points. So we can write that. So area equals to 1/2 PL by 4 EI, and your length of L/2. So this is our area we got between the 2 points. So that comes out to be equals to PL square by 16 EI. So we can say theta C, but from the analysis we say theta C is equals to 0. Isn't it? Theta C equals to 0. Here the theta is 0. So we can write theta C equals to 0. So we are left with minus theta A equals to this one. So your theta A is minus times PL square by 16 EI. See, we got minus. What does this means? Say here we got that this is also equals to, can we say that theta CA was positive? Can we say that theta CA was equals to PL square by 16 EI? Okay, but how is the representation of theta CA? See, theta CA was in the anti-clockwise. It was in the anti-clockwise, but your theta A actual is in the clockwise. That's why the negative here it came. It means that this negative means that theta CA was anti-clockwise, but your theta A is clockwise. That's why this negative is coming. And if you want to say what is the theta at B, you would get both. You would get both theta BC equals to theta B. That's both would be positive PL square by 16 EI. Say you have to draw tangent from B, then with respect to that you have that if you draw tangent from B, you would get this one. So your theta would be here a clockwise moment, clockwise theta. Okay. Let's have next one. Let's the next one. Let's have next one. This is our simply support beam. You are applying a point load at mid span. Say this is P kilonewton, that 20 kilonewton, and you want to find the deflection at this point. We call it point C. This is point C. This is 3 meter. This is 3 meter, and this is 6 meter. So you are applying load at the mid span. So your deflection profile would be somewhat, say ABC, and this point is your point D. Since the load is at the mid span, we can say it's symmetric loading. Can we say symmetric loading? And for the symmetric loading, theta is 0 at mid. Theta is 0 at mid, and delta is maximum at the mid. This is valid only if this loading is symmetric. So if we want to make the deflected profile elastic curve, we can say this is our deflected shape. We can write here, this is our delta D, that's delta max, and this is our this is our theta 0 point. But we need that deflection at C. We need to get the deflection at C. We need to get deflection at C and theta at C. Deflection at C and theta at C. Let's say that theta here is some value of theta C. So which point should we take reference for? Let's say we want to calculate delta C. Let's say we want to calculate delta C. Which point should we take reference? So say the reference point should be such that if it is theta is 0, we can then connect the 2 points and see what's we can directly then estimate that difference. We can directly say what's the difference of that delta between the 2 points. If the theta is 0, that means that line its deformation would be its deformation would be 0 based on the line if you draw tangent from that line. Say if the theta is 0, that means if you draw tangent from that line, we can say deflection would be 0 with respect to that line at this point. So based on that fact, if we take point D as a tangent point or reference point, so we draw a tangent from D, then we say that how can we get the delta C? How can we get the delta C? So if we see delta C, we can get if we know this value, and if we know this value, we can get delta C. We can write delta C equals to something minus something. Something minus something. What is the notation of this one? So this one is we can say this is delta at A, but it is with respect to a tangent drawn from D. Similarly, this one is your delta at C with respect to tangent drawn from D. So we got these two values. So if we know these two values, we can get the delta at C that we have to solve. So we can write delta at A with respect to the tangent drawn from D minus delta at C with respect to the tangent drawn from D. So what is the value of delta at A with respect to D? That's moment of area between the 2 points A and D, but centroid should be about point A into area. We can write area AD. Then we subtract it by centroid of the area, but point is about C. Centroid should be about point C into area between point C and D. So this value we have to get. We need to get the centroids and we need to get the area. So let's say you have a beam, simply supported beam, and a UDL is acting at the midspan. We have the BMD. Then we get the M by EI equals to PL by 4 EI. This is our PL by 4 EI. That equals to value of P here is 20 kilonewton. Length is total length of 12 meter and 4 EI. So we get 60 by EI. Some unit would be there. We get 60 by EI final. 60 by EI. So this is our 60 by EI, and it's for length of 6 meter. It's for a length of 6 meter. So point C is somewhere here. So this one is your 3 meter, and this one is your 3 meter. Can you get the value here? Can you get the value of M by EI value here? What should be the value of here? That point. By the similar triangles, can you say that for 6 meter it is 60 by EI? So for 3 meter it would be 30 by EI. Can we say that? So we can get so this is point A, point C, point D. We need to get the area between A and D. Area between A and D is we can get the area between A and D. That equals to 1 by 2, 60 by EI into length of 6 meter. And the centroid is somewhere here. We need to get the centroid for this part. Let's say this was your area. This was 60 by EI, and this is 6 meter. About point A, you need to get the centroid. So this is our centroid, that 2 by 3 of 6, 2 by 3 of 6. Similarly, you need to subtract by XC. That's you need to get the value of centroid XC. But before that, you have to get the value of area between A and C, that's C and D. So this is our area. And you need to get the centroid about point C. So centroid is somewhere here. You need to get centroid about point C. This is our XC dash, XC bar. So let's say you have a trapezium. You have here A, you have a value of A here, you have value of B here, you have length L. You need to get the centroid about this point. Let's say you want to get the centroid from this point, from A point. So we can say centroid from A point equals to 2B plus A by A plus B into L by 3. Yeah. Similarly, we can solve here. This was your 60 and this was your 30. You can solve for this part also, delta CD. So we can write this was your area 30, 60. EI, let's say EI was here. And length was 3 meter between point C and point D. So centroid here would be somewhat at a distance of XC dash, that we can calculate XC dash equals to, that we can calculate as that 2 times 60 by EI plus 1 times 30 by EI divided by total time is that 60 plus 30 by EI into length of L by 3, that's 3 meter by 3. And if we got this centroid, you have to multiply with the area of the trapezium, that's parallel side is sum, that's 1 by 2 parallel sides, that's 30 plus 60, 30 by EI into length of 3 meter. So you got the area between the 2 points. So the value comes out to be equals to that some value of 135, some value. Your delta C comes out to be equals to 495 into some units of some kilonewton meter square, some kilonewton meter square into meter divided by in EI. Your EI value should be known to us. Then we can directly finally calculate what should be the value of deflection at point C. Do you understand the problem? Okay. Now next step is that you need to get theta C. You need to get the theta C. You need to get the value of theta C. You need to get the value of theta C. So we can say, can you get the value of theta C anyway? Can we get the value of theta C? We have that theorem one, that theta forward minus theta backward equals to area between the 2 points. So if I want to say delta DC, we have to find that C, but your reference should be that D also. So if you take delta DC, that means delta at D minus delta at C. We have to calculate this part. So this value means that deflection at D with respect to tangent drawn from C. Actually, delta at D is 0, but if you draw tangent from C, there is some deflection. And we want to say what's that value of that slope. Sorry, slope was there. Okay. So if you draw tangent from C, you have to draw tangent from C. So this is our tangent from C. This is our tangent from C. Now here the theta is 0. So this is our reference. This is our point that theta C equals to 0. Theta D equals to 0. Now you have to say what is the value of theta DC. That means theta at D from the line, that tangent which is tangent to tangent to point C. So this is the value that theta DC. This is theta D minus theta C. So we can write theta DC equals to theta D minus theta C. But the value of theta D actually is 0. Actually, the value of theta D is 0 minus theta C. So finally, if your theta C was clockwise here, but the theta DC is anti-clockwise, that's why your theta DC came out to be negative times theta C. So that equals to area between the 2 points. Your area was somewhat like this, 30, and here was 60. Length was 3 meter divided by EI. So we can calculate that area, 1 by 2 parallel sides, 60 plus 30 by EI into length of 3. So we can get 90 plus 1.5, that's 135 by EI. And some units of that, units of meter here, the kilonewton meter. So we can get kilonewton meter into meter divided by EI, some values of E and I. You can calculate that if the values of E and I is given. So we can get the value of theta DC equals to this, but actually the theta C would be, that comes out to be negative times minus 130 by minus 135 by EI. So if your, that means if your theta DC was coming out to be anti-clockwise 135, that means your theta C would be minus times 135. That means if it was anti-clockwise, this one should be clockwise net. So we can see that theta here is that clockwise 135. Yeah, let's go to the next problem. Next problem is that let's say you made a, let's say you are having a some loading, then you made a BMD such that it was some variation of, let's say it was some parabolic variation in this fashion. Actually it should have been this way. So this is our BMD. We know that for the BMD we have area equals to 1 by 3 of B into H. Here the theta should be 0. Theta should be 0 here. Only then you can apply that area equals to this one. But let's say that because of the EI changes, that somehow it was going in the same fashion up to this point, but after that there is a EI change such that it raises by some amount. Then after that it reaches to the same point such that theta is 0. Here the theta is 0. Then if you want to say what's the area between the 2 points, if you want to say what is this value of area, this one, can you say this is 1 by 3 of B into H? Actually we can't say. We can say this area is not equals to 1 by 3 of some B into H. So this is your capital B into capital H, and this is your small b into small h, this value. We can say this is not equals to, because your theta here, it's not 0. But here you can say for this part you can apply that this area is 1 by 3 of BH. For we can say this is parabolic curve, 2-degree curve. Understand? The theta should be 0. Only then you can apply that 1 by 3 of BH in case of parabolic sprandle. We call it as a sprandle, nth degree sprandle. Now we have a cantilever, that property cantilever. We can also calculate the redundance using that moment area method. So you got a property cantilever and a reaction. Let's say the reaction here is B based on the loading, because loading is acting downwards. UDL for length L. This is point A. You need to get the value of reaction B, and you need to get the value of theta at B. So deflection profile is somewhat this way, theta at B. But compatibility is that theta at B equals to 0. This is compatibility condition. We have to ensure that theta at B should be 0. So if you know the BMD, then M by EI diagram, because of these two effects, that one is your reaction and one is your UDL. If you know that area between the two, then get the centroid and then equate that to 0, because your delta at B should be 0. Then we can get the reaction B. Let's make them as a primary beams or determinate beams. Let's say we only check the effect of UDL first. So the moment developed would be WL square by 2. Then you divide by EI. So we can get the M by EI diagram. This negative anti-clockwise moment, negative. So here the shear force is some value. So theta is not 0. Then here the theta is 0 because shear force is 0 here. Then you join them by 2-degree curve. Okay. Similarly, you have a simple same beam, but you are applying load of B upwards. So your BMD would look like a linear variation of that B into L, then goes to 0. This is 1 degree. So we got these two values. This is positive, this is negative, and And finally, you have to make sure that at point B, deflection has to be 0. Let's say because of this, it deflects downwards by an amount of we can write it as delta B1, and this one it goes upwards by delta, we can write it as delta B2. But let's say you also want to calculate it by moment area method. It says that draw a tangent from a reference point. Let's say A is our reference point because theta is 0 here also, and delta is 0 also here. So it is our tangent at A. Similarly, this is our tangent at A. So if you draw tangent at A, then you say, what is this value? We would say, hey, this value is equals to deflection at B, but it is with respect to you draw the tangent from A. Similarly, this value is also equals to deflection at B with respect to the tangent drawn from A. So we can say that delta B1 is similar to delta B with respect to A. So that equals to centroidal distance between about the point B, and you multiply it with the area. So we can say, what is the delta B net? We know that delta B net equals to 0. That equals to delta B1 plus delta B2. But based on that moment area method, we say delta B1 equals to delta B with respect to A. We can name it as delta B1 with respect to A. Similarly, plus, and this one equals to delta B2 with respect to tangent drawn from A. So we name it as delta B2 with respect to tangent drawn from A. So that equals to, we know that equals to centroid distance of xB1 into area 1 plus xB2 into area 2. Can we write it as this way? Yeah, what's the area of this parabola? So we can write it, then the area of this parabolic spandrel is equals to, now we can calculate the area of this one. So area here is equals to, we can write the area equals to that 1 by 3 WL square by 2 EI into length of L, and the centroid is acting at, from the point B, centroid is acting at, say this one is your L by 4. For the 2 degree, this one is your L by 4. That equals to L by n plus 1. Yeah, this is L by 3, yeah, n plus 2. This is L by 4. Your n is here, n is equals to 2. So it is L by 4. If this is L by 4, this one it would be 3L by 4. But the value here is negative. BMD is negative, so write minus times. So we got the value of delta, that xB1. We got this value xB1 A1. Now we need to get xB2 A2. Similarly, we can get about the point B. We need to get the value of centroid. So this is a triangle. We can get that centroidal distance would be 2 by 3rd of L, and the area between the 2 points is 1 by 2 B into L, and your centroid of 2 L by 3. So that becomes equals to BL cube by, and you have to divide it by EI because we are dealing in the M by EI diagram. So by EI, so we can write 6 EI. BL cube by 3 EI. BL cube by 3 EI. So we can say plus BL cube by 3 EI. That equals to delta at B. This is equals to 0. So we can get the reaction at B equals to that 3 by 8. 3 by 8 of W into L. So we got the reaction at B equals to 3 by 8 of W into L. 3 by 8 of W into L. Now we need to get the theta at B. So once you got the reaction at B, there is still some theta developed at B. So we can say that is the difference between the two. That is the difference between the two effects when you superimpose the two effects. Let's say that removing these centroids, we can say see here the theta was some value of theta was there. This was our theta. You can write theta 1, and the theta here was developed some theta 2. It was it was acting in the, say, this was this theta, first theta was acting in the clockwise direction, theta 1 clockwise, but the next one was acting in the anti-clockwise, theta 2 anti-clockwise, theta 2. So your theorem 1 says that theta forward minus theta backward, that means theta BA, that means you have to draw tangent from point A. So if you draw tangent from A, then you say, what's this value? This value, that's in the same direction as that of theta 1. So we can write that theta we can write here point B, we can write theta BA equals to theta B minus theta A. And we know that theta A equals to 0. That means this equals to theta B minus 0, theta B minus 0. So we get theta B. That equals to area between the 2 points. We know that area equals to 1/3 WL square by 2EI into length of L. But the value of E, this diagram is negative. We can write minus times. So we get theta B equals to this value. Similarly, we can get the theta B2. So we need to get the value of theta forward, backward. So this is theta forward minus theta backward. So here we can write here your forward point is B. So we write theta B minus theta A. So theta B minus theta A. So you have to draw tangent from A, and you say your theta 2 is in the anti-clockwise. So if you say from the reference point tangent at A, your theta BA is also anti-clockwise. So that equals to theta B minus theta A. So difference between the two, that's equals to M by EI between the 2 points diagram. So we can write theta 2 equals to 1/2 your value of BL by EI into length of L. But the reaction we got the reaction B equals to 3L by 8. So this is B 1/2, 3L by 8, 3L by 8, 3WL by 8 into L square by EI. So we got 3/16 WL cube by EI. Yeah, 3/16 WL cube by EI. But this is positive, first one is a negative. So theta net is sum of 2. Theta net is equals to 1/6 plus 1/16. Is it 1/16? 3/16. And common is equal, common terms are WL cube by EI. So 6 inverse and 6 inverse minus 6 inverse plus 3/16. 1/48. So final value of minus positive value of 1/48 WL to the power 3 by EI. The final value of theta net equals to this one. So we got positive value. That means the first part was clockwise. See, effect of this one was clockwise. This was clockwise, but it was negative. So but final value we got positive. That means final net value has to be anti-clockwise, because your next term was positive, this term was positive, because positive means it was in the anti-clockwise. So final value should be anti-clockwise theta. So if you see from the analysis also, we can say theta B is net value of WL cube by 48 EI. Yeah. Now we will take that. We take fixed beams. If we take fixed beams now, say this is fixed beam, but the loading is that it's having UDL for the entire span, WL. So we need to get the value of moment developed at the ends, that we call as end moments. And after that, you can calculate the value of delta max also. Since loading is symmetric, we can say delta, and we can say theta is 0 at mid. It is one conclusion. If the loading is symmetric, theta is 0 at the mid. And we can say from the compatibility that delta is 0 here, delta is 0 here, theta is 0 here, theta is 0 here. So let's name them as A and B. And since the loading is symmetric, we can say as loading is symmetric, if the loading is symmetric, we can write moment developed at A should be equals to moment developed at B should be equals to some moment of M. And if you do superimposition and you make two simply supported beams that's having that, let's say it's a simply support beam. Let's say the moment developed here is M and moment developed here is M. Say if you write it as M and M. Similarly, you have a simply support beam. This is your that external load that you are applying, W for length L. If you want to make the that separate BMD, so for this one the BMD would look like a straight line, a constant line, that ML by EI. Okay, right, M by EI. This is negative because your moment is anti-clockwise, hogging, so minus M by EI. And similarly for this one we have that standard result. We can write the maximum moment is at the mid, that equals to WL square by 8, but this is divided by EI and positive. And this is a 2-degree parabolic, we can say. This is a parabolic variation, 2-degree, WL square by 8, EI. So we got these two values. Now how can we solve this equation? Let's say that this was your support, and because of the loading, say here the deflection at theta is 0, then there is some deflection at the mid, and here is also theta 0 and delta 0. So if you write compatibility condition in terms of theta, let's say that you draw a tangent at A. This is tangent from A, and you want to say what's the theta at, point B. Can you say? But actually theta A is 0, theta B is also 0. If you draw tangent, they will pass in the same line as that of A and B. So we can say, we can write theta at B with respect to the tangent drawn from A. We can write in this fashion that theta B with respect to the tangent drawn from A, that equals to theta B minus theta A. And we know that theta B equals to 0 and theta A is also 0, that equals to 0. So if you get the area between the 2 points, that should be equals to 0, and you equate, and you can get the value of moment developed at the mid and moment developed at the end supports. So this is length L, this is length L. You can get the value of this area between the 2 points. So we can write M by EI, but it's negative, into length L. This is area 1 plus area 2 is equals to, we know that for the parabola, area of the parabola, that if this is your parabolic variation, area would be 2 by 3 of B into H. So we can write 2 by 3 of WL square by 8 EI into length of L by 2, and we have this L by 2 and this one also L by 2. So we can write it twice. So this overall value should be 0 because our theta BA was 0. So finally you can calculate that M comes out to be equals to WL square by 12. So the moment developed is positive. Positive means the direction you assumed that theta here is M in the anti-clockwise and in this part clockwise. That means that's true, that you assumed that theta is this in this fashion. So finally you got moment equals to WL square by 12. So you got the moment is developed at the ends, that equals to WL square by 12. Now you want to say what's the delta maximum. From this figure we can say delta would be maximum at the mid. Delta is maximum at the mid. So we can write it is maximum at the mid. So if you want to say what's the, if you want to say what's the, how can you solve that? Let's say you want to apply the moment area method theorem to, that says if you know one reference point, you draw a tangent from that point A. Let's say our reference point is tangent from that point A. A is our reference point, we draw a tangent from A, and you want to say what is this value equals to. We say this is deflection at mid, but it is with respect to the tangent drawn from A. That's also equals to the delta maximum based on our NA that experience. We can say this is also a delta max. So this is delta M with respect to A, but we know that delta maximum, delta at mid with respect to A equals to centroid of that area about that point mid into area between the 2 points AM. Is it from theorem 2? So once you got the centroidal distance between the two and area of that, then you multiply them, get the value between that delta max. So you need to get the delta maximum at the mid. So you only need to get the area between the 2 points, that's A and point M. You only need to get these 2 points, area between these 2 points. So this length is L by 2. Similarly, this length is L by 2. This is point M, this is point A. You only need to get the area of this one. So we can have, since we can remove this part, okay, this part we can also remove. So we know that area is also given there. This one is your area of this part. M by EI into length is L by 2. So we can write L by 2. But the centroid is from, centroidal distance should be from point, centroidal distance should be from point M. So this is L by 4. L by 4. Similarly, this is your area, that 2 by 3 of B into H. Okay, length is also same, L by 2. Then the central distance is that from this point, you need to get this value, we know that for the centroid, for this parabolic variation, we have this value equals to 3b by 8. This is 3b by 8. 3b by 8. So we have this one, the rectangle, and we have that this one was your 1 by 3 of BH. This is 2-degree curve. The centroid was here B by 4, and the centroid here was, in this part, it was 3b by 8, and the area was 2 by 3 of BH. So this area, it is this one. So the centroid is 3b by 8. So we write 3b by 8, your B equals to L by 2. So you substitute the value of M. The value of M equals to WL square by 12. And rest you calculate that this is L by 2 EI, L by 4, then plus that dash, and that equals to, we can say that equals to delta at, we can write that is equals to this value, final value, it is equals to delta at mid with respect to the tangent you draw from A. And that is also equals to delta at mid, because delta at A equals to 0. So finally you got delta mid equals to maximum, delta maximum. That comes out to be equals to some value of, that will be equals to 384. WL to the power 4 by 384 EI. And if you have a simply support beam, that if you have only this part, this is UDL. If you want to say what's the maximum deflection, we know that deflection would be maximum at the mid. This is deflection maximum. We say that get that value of this one. So we draw tangent from here, and you calculate this value, delta AB. This value, when you calculate this delta, that you have to say this, that equals to area between the 2 points. So this area, that is equals to WL square by 8 EI and 2 by 3 of L by 2. That you calculate, and you check the centroidal distance, that is the central distance between the 2 points. That equals to 3 by 8 of L by 2. 3 by 8 of L by 2. That comes up to be equals to 8 inverse into 3 inverse into 16 inverse into 3. WL square by 8 EI 2 by 3 L by 2 3 by 8 L by 2. It should have been equals to 5 by 384. The deflection for the simply support beam subjected to UDL, that value should be equals to 5 by 384 WL by WL power 4 by EI. But your value here in the fixed beam having UDL, that comes out to be equals to 1 by 384. That means it has reduced by 1 by 5th of that value, delta simply support beam. Actually, there is some correction. We can see that later also. It's not coming over that 5 by 384. 8 inverse, you can say 2 by 2 by 3 divided by 8 into 3 divided by 16. It's coming out to be WL to the power 4 by 128 EI, but it should be equals to this one. That is the later part. We can see it later. That's not our issue now. We can see our problem was that this one we got this delta max, but its value equals to 1/5 of that delta simply support beam. Yeah. Let's take the same fixed beam, but the loading is a point load at the mid span. Let's take that this way. Loading should be at the mid span. This is L by 2, L by 2. So loading is symmetric. We can say deflection would be maximum at the mid span. So this is delta max, and theta is also 0 here. This is valid only when the loading is symmetric. So we need to get the moment at the ends developed at the ends and the delta maximum. So on the similar grounds, we can say, as we earlier saw, that let's say the moment developed here is m. By the symmetry, moment A equals to moment B, that we say that is some value of m. Then the m by EI diagram looks like this one. Similarly, for the simply support beam, you have point load here, so we can write PL by 4 EI, PL by 4 EI, PL by 4 EI. This is positive. So if you want to say, if you write the condition that if you draw tangent from A, then you write that theta B A, that equals to theta B, theta at B with respect to tangent drawn from A, that is theta B minus theta A, that is 0 minus 0 equals to 0. That's the area between the 2 points. From theorem 1, we can write minus m by EI plus area of this curve. Area of this curve, that's 1 by 2 into PL by 4 EI into length of L, that equals to 0. We can write that moment developed at the free end equals to PL by 8. PL by 8. So once you got the moment developed at the ends, that equals to PL by 8, then we can write, now we need to find the delta at the mid. For the delta at the mid, we need to take that area between the points A and B, A and mid only. This is point M. So we need this area, and we need this area only. And say centroid from mid is equals to this one, that's L by 4, and centroid for this one is 2 by 3rd of L by 2. 2 by 3rd of L by 2. So we can calculate that. So this is your area is m minus m by EI into L by 2 into centroid of L by 4 plus 1 by 2 PL by 4 EI into length of L by 2 into you multiply it with the centroid distance, that is 2 by 3 of L by 2. Then you calculate that. You substitute the value of m equals to PL by 8. You would get delta at mid. We can write that as delta at mid with respect to the tangent drawn from A, that is also equals to delta mid, that equals to delta max, that equals to PL cube by 192 EI, that is also equals to 1 by 4 PL cube by 48 EI. We know that delta as we earlier calculated for the simply support beam, that you have point load at the mid, delta maximum is at the mid, that equals to PL cube by 48 EI, and this one is 1 by 4th of delta simply support beam, that this one. So next one problem, that now we don't want to apply the moment at the mid span exactly. We say let's apply at some length A from support A. Let's say you want to apply a load of P at some length A from support A and B from support B. Let's say that A is greater than B, and which implies that moment developed at B would be greater than moment developed at A. Let's say for some instance, we can say let's say the moment developed here is MA, moment developed here is MB. We can make the free body diagram that we can make two beams that, let's say moment here was MA negative then you divide by EI, and here there's some moment MB by EI, that's also negative, and you join the two because let's say you have a split support beam, you apply a moment of M, we know that reaction, here the reaction developed would be M by L, and here would be downwards M by L. So a shear force diagram would be somewhat this one. So similarly, on the similar basis that here, let's say M is net MB minus MA, here is some net value of MB minus MA here, because one is your anti-clockwise, next one is your clockwise. So then the final variation would be a linear variation between the two, because shear force diagram is x to the power 0 function, so your bending moment is x to the power 1 function. So you have this diagram, and similarly you can have next diagram of that one, PB by L, PAB by L. This is your bending moment diagram. Then you divide by EI, so you get the value of PAB by L, EI. By the similar trend, we can say that theta B with respect to the tangent drawn from A, that is theta B minus theta A, that is equals to 0 minus 0 equals to 0. So this is our deflection profile somewhat this way. So then we draw tangent from A, then we say that theta B equals to 0. Okay, that equals to area between the 2 points. That equals to area between the 2 points. So let's calculate the area between the 2 points. So we have that trapezium, area of the trapezium equals to 1 by 2 MA plus MB by EI, some parallel sides into length of L, but overall value of this one diagram is negative, we can write minus, and we have this value that this is positive that triangle, 1 by 2 PAB by L EI into length of L. We know that L equals to A plus B. Okay, L equals to A plus B. That equals to 0 because theta B A equals to 0. So after substituting that, you get the value of moment, sum of end moments equals to PAB by L. That equals to free BMD. So if you see here, we have a free BMD value of PAB by L, that equals to sum of the end moments MA plus MB. In the previous case also you have that load was acting at the midspan. So here the moment developed was MA, and moment developed here was MB. We rate MA equals to MB equals to M. That we calculated it was equals to PL by 8. But if we say from the free BMD, we have maximum value of PL by 4. So we can write twice MA equals to twice M equals to PL by 8. So your M we have that we can write that in terms of this one, MA plus MB equals to PL by 4. We want to check whether this is exact equals to this one. So we have MA equals to M, that was PL by 8 plus PL by 8, that equals to 3 BMD of PL by 4. Okay. So finally we got one equation. We got equation between MA and MB in terms of PAB by L. So next equation, if you want to say for this case now loading is not symmetric. See, in the previous two problems we said that loading was symmetric, but in this case loading is not symmetric. So if the loading is not symmetric, delta cannot be maximum at the point load, is not maximum at point load. So this is an important statement, that if the loading is not symmetric, delta cannot be, it can be or it can't be. We can't directly say that delta is maximum at the point load or at moment where bending moment is maximum. We can't directly say this statement that if the delta is maximum, if the loading is not symmetric, we can't say directly that delta would be maximum at the point where the point load is acting, or where the point that bending moment is maximum. We can't say that statement. So we need to see next condition using the fixed supports themselves. We say that in the first case we said that theta BA equals to 0. Let's say now we want to say delta A and delta B is also 0, because this is one more compatibility condition. Here the theta is delta is 0, delta is 0. So if you draw tangent from A, then we can say tangent from A, if you write delta at B with respect to tangent drawn from A, that's delta B, that's equals to 0 because both are 0. So if you use this equation, this condition, then you can solve for the next condition such that you have two unknowns and two equations. So next statement is that we want delta B with respect to A. So we want centroidal distance about point B. Let's say the centroidal distance of this one would be at point so let's say the centroid would be at here. We can calculate that x b, and similarly centroidal distance of this one would be here, and this one would be here. So this is point B. So we want to get this value, and we want to get this value. We can say this value, this is equals to 2 by 3 of B, and this one, this is equals to B plus A by 3. We got these two values. And what about this one? This is trapezium. You can either convert it into triangular and rectangular plate, that area, or you can do directly by trapezium. It's up to you. Let's say we got one equation, that we got this equation, and next equation we have to make. So we can write that. Let's write equation in terms of we can say the area between the 2 points, that's 1 by 2. That's already, we know that this is the area, 1 by 2 MA plus MB by EI into L. This is the area. This is negative overall. Overall value is negative, and we have to get the centroidal distance from the point B. So we can say the equation was equals to that. We can write 2 MA and plus MB divided by MA plus MB into length of L by 3. But the thing is, yeah, we can write it. So this one and this one will get cancelled. So finally we can write it as minus L square by 3 minus L square by 3, minus L square by 6 minus L square by 6 EI, and you have 2 MA plus MB. Yeah, we can write it as in this fashion also. So we got the first part. Now we need to get the next part. Now we need to get that moment of this area also about this point B. Let's say for the first part we write 1 by 2 PAB by L EI, and length was, say this length is A. We write A into centroid about point B, that's B plus A by 3, and similarly 1 plus PAB by L EI, and the length of B, and centroid is equals to 2 by 3 of B. Now you calculate it. Say we can see what's the common terms. We can keep them common. So we write that 1 by 2 PAB by L EI. So this is common, that PAB by L 1 by 2. This term we can keep the common. Then we are left with AB plus A square by 3. Then in this part we are left with plus 2B square by 3. So let's keep that 3 also common, that this 3 also common. So we can write 3, and we can write 3 into 2, that's equals to 6. So we can have this one. Finally we can write it as this way. So finally we have this equation, that PAB by L, PAB by 6 LEI, this one, and we have one more equation, that this one. So we can copy it. So we got this equation that the, the condition is that, yeah, overall value, the theta, we know that the condition has to be that theta ba should be equals to 0. So if one of the terms is negative, see, this part is negative and this is positive, so we can equate it to 0. Then finally we can write this should be equals to this one. Can we write that this should be equals to this one? Now see, here the length is that ei into 6 and ei into 6, it gets cancelled, so we are left with that we can write 2ma plus mb equals to pab by l cube. That's l square into l, that becomes l cube. Then we are left with, let's make this function in terms of a plus b, because a plus b equals to l. Then we can cancel one of the l lengths. So let's write in terms of a plus b. This term we have to write in terms of a plus b. We write then 2b plus a. Then we can become it becomes equals to these three terms. So we can write a plus b into 2b plus a. The thing is that you have to just remember the result then at the end. That's your goal. So we can write 2ma plus mb equals to pab by l square. This is one of the l gets cancelled, so we write 2b plus a. Now we know that from the first result that we have from the theta b minus theta a, that this one, summation of moments equals to pab by l, summation of end moments equals to pab by l. So if we substitute here, that we can write it as ma plus pab by l, this one 2 times that, so equals to this one pab by l square 2b plus a. So after simplifying, you get moment of summation that moment a equals to pab square by l square, and summation of that moment b equals to m that pba square by l square. These two values you get at the end. Now we have one more problem. Say we got one more problem we can solve. Now this problem is about the internal hinge concept. Here is an internal hinge at point B. Then after that there is a point C where point load is acting, a load of P, and after that you have a roller support at D. This is L by 2, this is L by 2, this is L by 2, this is support A. You need to get value of deflection at B, deflection at C. You need to get the value of deflection at B and deflection at C. There is an internal hinge at B. So let's make the free body diagrams. Say the direction here is D, and here a load is applied at the midspan. So let's say the shear force here is V, that would be transferred by the hinge into this in the opposite direction. Say this is shear force V. We want to say what is the value of the shear force. Since the loading is symmetric, that load is at the midspan, we can say the reactions would be P by 2 and P by 2, and same would be transferred to this one. So let's make the BMD of these two profiles. We say this one is your BMD. That's the value is equals to P by 2 into L by 2. That's P into L, because your load is P by 2 and length is L by 2. So it becomes the moment PL by 4. Then you divide by EI. So you're left with PL by 4 EI. And this is negative because it has developed anti-clockwise moment of PL by 4 EI. Then length is L by 2. And similarly, you have a free bending moment diagram of that PL by 4. And you divide it by EI. So you are left with PL by 4 EI. Yeah, we are left with this one. This is positive BMD. Now based on this fact, that this is hogging bending moment, and this is your positive sagging. So if you want to make the deflection profile, let's make the deflection profile. Say that this point, based on this, if this part AB, if this part A, B, C, D, if this part AB is getting hogging moment, that means the deflection profile is a hogging curvature up to this point B. Let's say after that, we know that for the internal hinge, at internal hinge, delta should be same between the two segments. Delta is same on both the segments. Delta should be same. If this is delta here, then this part also has to go down by same amount. So such that the connection is valid till that point also. You have to ensure that connection is as it is. So this is the this would have been delta C. This would have been delta C if there was no load. But the BD is also having some load of that P. Because of that, there is a bending moment of PL by 4 at the point C, so that there would be some curvature. Let's say after that there would be a curvature of sagging curvature, so your change would be there. So this is our sagging curvature, such that this is delta 2, where delta 2 is because of load in BC, and delta C equals to delta B by 2. It is because of straight line effect. Because of straight line effect, delta C equals to delta B. If we see by the similar triangles that if it is delta B, this one would be delta C equals to delta B by 2, because your length is L by 2 and L by 2. So you need to get the value of delta B. For the delta B, let's say you get the value of delta B. For that, let's analyze this part, that this is a load P by 2 and deflection profile is downwards. So if you draw a tangent from A, you get the value of this one equals to delta at B with respect to the tangent drawn from A. This is equals to that center moment of that area between the 2 points about the point B. So this is your XB bar. So this XB bar equals to 2 by 3rd of L by 2. So we write 2 by 3rd of L by 2 into area between the 2 points. That's 1 by 2 negative PL by 4 EI into length of L by 2. And this is equals to delta at B with respect to tangent drawn from A. This is also equals to delta at B. So delta at B equals to minus times PL cube by that comes out to be equals to 48 EI. You can check it. So PL cube by 48 EI is the deflection at point B. So you got the deflection at B. Now you need deflection at C. That deflection at C, that means total deflection at C. So total deflection at C is the delta C plus delta 2. So we can calculate that delta 2 from this figure, that if you have a simply support beam, subjected to point load P at the midspan, and this is point B, point C, and point D. Say we know that for loading symmetric, the deflection is maximum at the mid, and theta is 0 here. So if the theta is 0 here, you draw a tangent from this point. So draw a tangent from point C. So this value, we know, we have already calculated this question also, that this one is your delta B with respect to tangent drawn from C. This is also equals to delta C, that we denoted as delta 2. So we can write it as it is also equals to delta 2. So your delta B with respect to C equals to area, that centroidal area about point B into that area between B and C. What is the area between B and C? This is your point B, this is point C. So this is total area between the point B and C. So that area equals to PL by 4 EI, length of L by 2. So area equals to 1 by 2 PL by 4 EI into length of L by 2. So this is the area, and you have to multiply it with the centroidal distance from point B, because you are calculating about point B. So your centroid should be about from the point B. So this is length of XB, that equals to 2 by 3rd of L by 2. So right, 2 by 3rd of L by 2. So this value delta 2, this also comes out to be equals to PL cube by 48 EI. So this value is also PL cube by 48 EI. So the final deflection profile is, so we can write delta at C total equals to delta at B divided by 2 plus delta 2. This one was your PL cube by 48 EI. You divide by 1 by 2, say you divide it 1 by 2 into, then we write next one is your PL cube by 48 EI. So final value of PL cube by 32 EI downward would be deflection at C.